Okay, hello. I'm back. Thanks again for being here, looking at over 40 people in the participant list. So this is the first actual content here of this this event. We have 15 slots of 1 hour each total, 3 each day. So this is the middle hour for Monday. The third hour will be Toby talking on Pforest and Petsy. So what I'll do in this tour is okay, well, thanks. I'll skip the intro then and begin with session 1, which is a tour of the software and what it can do. And I'll begin at the beginning more or less, but it will be somewhat random since I tend to explain certain things that I just run into there, which is hopefully good since many of you have done some of the groundwork here, but not all of the aspects of each of even the earlier steps may be clear or well documented by us. So hopefully just going through these things myself is maybe exactly how you do it, but maybe it's also different, and then we can think about which way is maybe better or more efficient. So if you actually think that there are better ways to do things than I do them right now, which is absolutely possible, then please say something, right? So I want this to be interactive if it can be, or if it makes sense, which means all the time it makes sense. So please just pop up your picture and microphone even without me inviting you. If there's anything you want to contribute or to correct or add or give me another perspective, since I think the audience can benefit a lot from interaction from multiple points of view, and I'm also looking forward to all of that. And if there are things coming up that I really need to do differently, then I'll be happy to keep them in mind, right? To make things even better for everybody. So how would we begin? Pforest is both a software and algorithms. The question is what comes first? We don't really know historically. Of course, what you see in the repository is the first commit. If you want to look at GitHub here, let's share the screen. So this is my official Pforest repository at the GitHub site here. And if you want to go all the way back in time, let's 2,700 commits. And could we go all the way back down? Who knows? Probably not easily. That would probably be done with another viewer like this one. I'm not sure if you have used GitK in the past. There are alternatives. So this is just a repository and history viewer. So if I go all the way down here, then we're looking at 2007, November 23rd, and we began with the beginning in a sense, and mostly because Lucas and I I ran into Lucas's office with some ideas, and Lucas had some better ideas, and then we kind of sat down and did a whole bunch of pair programming, and that's how everything started. I'm telling just a little bit of this story in that SciAm news article I was invited to write lately. So if you want to check that out, it's linked somewhere on my webpage. So yes, getting the software. So how would we go about that? Let's just make a directory. You can see this window okay, I hope, right? So if it's not big enough for you, you can maximize the big blue button window here with this icon in the top right. And then let's just check this out from the repository, right? So we have the link up here. And just grabbing it, it's not all that big. It's just in terms of lines of code, it's around 50,000, I guess. So Nah. So that's it, right? And you see that we're using the autoconf style of setting up the software. Many people these days use CMake. I think that this is still sufficient. There's no real need to do it any different. But of course, if anybody wants to just submit a pull request with a complete CMake conversion, we will be happy to look at that. Both systems can coexist in the same source tree, which is important, right? So what we see here is that we do not have any configure script yet. If you get this from the source, there's this bootstrap script which basically just calls a couple of those autotool things to put these scripts together. I'm not sure how many people have actually ever done any autoconf scripting, but first of all, in terms of branches, we have the develop branch, which is the most active and the most current in terms of stability also. So it is usually a lot newer than master, but still we only put things in develop that we trust. So if you want to work with develop, it is generally a pretty safe choice to use. There is the develop branch, which has a bunch of dependencies that we used in the beginning, such as the dependent we can pull in BLAS and LAPACK for, not because we use it, but because other application would use it. We have a couple more dependencies on, say, GNU OpStack and things, and Fortran compiler comes in and so on, and this works usually, but some people run into issues, understandably, given the diversity of systems. So that's why there's this branch pre v3, so this is just before we get to version 3. Right now everything is version 2 in this sense, where I've stripped a whole bunch of these things that just get in the way. So no more Fortran, no more other dependencies here and there. So this is the branch that I would use. Another thing to know is that we have the subdirectory sc. That is actually another Git repository for a self-contained library. It has certain helper structures such as arrays, hash tables, things like that. So after checking out Pforest, we need to populate sc, and in Git this is a submodule. We would have to call init and then update, which will actually doing the cloning, getting the software. So this is necessary if you get Pforest from source. Where's my git k here? Oh wait. So we have this call again, and we see that we're current. So if we go into the sc directory, we see that it's a whole other directory, and it has the same branch names that I put there, and this is all current. So now we can actually use Bootstrap. Since we're using autoconf, some of these files are M4 macros. That's a macro processor. That basically what it does is that that each macro expands into a whole bunch of shell scripts, and that shell script is run as part of this big configure shell script. And each snippet of shell script tests for certain features, for example, of the existence of a certain .h file and things. The sc library is built in the same way, and there are a couple of things that we always need, like checking certain MPI features. It's not that much anymore. In the pre-v3 develop branch, I've removed a whole bunch of things that were also a little more complex in the configure. So now that we have the subdirectory, let us run the Bootstrap script to put together. It basically runs the M4 macro processor that takes all these snippets of shell scripts and assembles them into one configure script. And this is done. See here, this is the result. It's a 5500 MK shell script, and the same exists in the subdirectory sc. And now we can just see what it does. So those of you who have used this before or compiled any arbitrary Linux package know all this giant output of this script, right? All of this is standard in the sense that every project that's using it will allow for options to configure where the really interesting stuff, except for here prefix, is interesting because this tells us where we want to do the make install, which directory that goes. If we want to work with the make install version, we should specify that. Right now it's for developing, it's not really necessary. You can fine tune these directories. And now we get into the actual Pforest configure options, which you see here, right? So there's this disable, enable, logic. For example, this is a feature if you don't want to write just floats into your graphics output but doubles, you would use that. Most of these you would not actually need usually. So Pforest comes with independent code as a binary for 2D and 3D, and you can choose to disable either if you want to. It doesn't really make much sense, but it's good for testing and having fun with it. P6 is an extension written by Toby, where we can have a 2.5 dimensional mesh, so to say. So we can have a 2-dimensional base mesh that is a conforming mesh of hexahedra that has some arbitrary shape, and then it can be extruded by a layer, and that layer can be refined horizontally and vertically. So this is exciting if you want to do pseudo-flat things. There's Mpi, which you should enable if you want to use it, but you don't need to. So Pforest runs fine without any Mpi. It will just always run on size 1 communicator. That's pretty much it. For debugging, I recommend to use disable shared, actually, not using this thing, because then you get line numbers and called stacks and all these things, right? Before I go further into the source, maybe I should step back and give you some idea what this whole thing is about in the first place. As I said, it's a software, but it's not a simulation software. It does grids, meshes, refinement structures, and if you want to simulate things, of course, you need discretizations, linear algebra objects, solvers, main functions, time steppers, things like that, which is not what we do. So the idea is to give a toolbox that does everything that you ever need for parallel meshing and the operations on the mesh that is changing dynamically according to the needs of the simulation, handling most of the parallel communication that is mesh informed, but other than that, just lets you do your thing in terms of your simulation. We have been using this for way over 10 years now. Maybe I can show you some movies here, right? So there is this movie that when I was still in, no, it was just after I left Texas, we and mostly, who did that? So we were working also on this earthquake simulation project as a joint effort, and we ran some simulations there, and then we created a whole bunch of graphics files that were processed by that really cool guy at the Texas Advanced Computing Center to make a video, and that is the result. So we just made this stunt with this earthquake simulation that is here. I'm not sure you can see this all that well. I guess not so much, right? So this is supposed to be a spherical picture of the globe with continent outlines and so on. I don't think it comes through very well here on the screen, but this is a simulation of seismic waves on a 3-dimensional but stationary adaptive mesh. So we were not doing dynamic meshing here. We were just using the refinement to first of all, using the Pforest being not just the box but any shape to make up the sphere out of deformed cubes, and then to refine according to the wave speed that is different throughout the globe. We have very slow wave speed at the top and very fast wave speed in the center of the Earth. So this is one really cool example. And then there's this video made by collaborators at UCSB, Frederick Guibou and his people. And they used Pforest for a semi-Lagrangian crystal growth simulation. Can you see this? Wait, where's... Yes, so this is pretty nice that we're tracking a surface evolution here with adaptive meshes that you can see how fine this whole meshing went, because they need to be very carefully resolving a boundary between a liquid and a solid to do crystal formation. So and they had a time stepper, and in every time step they were doing not just one refinement but multiples. And you see how recursive the whole thing is. So they could actually go in there and run a 8-level difference simulation here. And they were saving just about a factor 1,000 of computation, because they could be so strongly adaptively refined where they needed it with these crystal seeds, right? So thanks to the UCSB people and Frederick, who's also he's a participant, but he's not here right now. So thanks to you guys. This is a video that I really like to show, because the adaptivity obviously is really, really necessary to pull off this detail, especially around the curvature here. So you see all how big the level differences are in this resolution. Yes, I've never spent that much time in a single visualization, so that's awesome work. Thanks guys. So again, Pforest does just the mesh, but it does it in a way that we think is near optimal in terms of parallel adaptivity, in terms of scalability and absolute speed. So so maybe we can then go back to how this software is actually capable of supporting such simulations, with just a bunch of code files here, right? So we have just looked at configure. We have not started compiling it yet. We were just looking at the help screen here. So what I like to do is go into a different directory. Say I want to compile this version with MPI here. Yes. So this directory is empty, so I would like to call configure relative here, right? So you can do it that way. And then what would we need? We here we want to do an MPI compile. So to do that, I need an MPI compiler such as this one, but I usually don't like the compilers that come with the system. What I really like to do is compile Mpich, for example, which I did on my laptop, but apparently not here. Did I then? Probably not. But you may want to download your own MPI installation if you want to be sure that everything works. The one here apparently is good enough, so, but still. Regardless, we need MPI, and what I also like is always enable debug mode, because that checks tons of assertions all the time. So Pforest is a relatively bug-free software, I would think, because we just almost never find any. And And we think, or I think, that that's because we just use assertions on even the most trivial things. Since there's absolutely no reason, I think, to trust myself in programming, so nobody should trust themselves when they program, I think. And I try to catch myself with all these stupid things that I do, and that's why I state the very obvious in the code in terms of assertions. And it is surprising how often these assertions actually break and tell me, hey, you got this very obvious thing very wrong. And that's why this code is full of assertions, which are only enabled if I turn on debug mode. So of course you can turn this off if you want to be fast, but since we want to develop here and be safe, we would debug this. Another way to be conservative in terms of coding safety here is put in a couple compiler warnings like those, right? This depends on your actual compiler. I like to disable optimizations in testing and turn on debugging symbols to have the most, the closest binary to what the source is, so I can use inspection and debugging and looking at the source code from a running program using a debugger and so on. So we could just do that. So it's running configure twice, once from the SC subdirectory, once from the repository top level. And what this does is creating makefiles. So those makefiles were not there before I call configure. Makefiles are written by the configure script. And if I update my makefile in the source, like here, like this, for example. So we don't write makefiles, we write auto makefiles, which are very simple compared to actual makefile logic. This is not a good example, but we include things. For example, this thing in the subdirectory, and we just collect things that we want to compile, and then tell it if this goes into the library or what the C flags are and what the CPP flags are. So all this is this I think is a lot easier than writing makefiles myself. So now if I make, I would call parallel make because we want to be quick, and most of the compiles do not depend on other compiles. So if I begin doing that, you see a lot of stuff that nobody really wants to see. So what I can do instead is use this autoconf feature of adding v equals 0, the environment and variable v. I'm not sure many of you know this, but this basically disables a bunch of output, and all you see is one line per compile and anything that comes from the compiler as a warning or error. And we see that we have a whole bunch of warnings here, but that's because we're just not using a parameter passed into a function. I think this should not be a warning. So what we can do is disable this. And run configure again. This is reasonably fast, right? So I am getting a question here that the screen may not be shared. Everybody's seeing what I'm doing, right? Okay. So what you should be seeing is a camera picture in the bottom left and top left, all the text and title of this event. And on the right, you see a shared screen with 2 terminals and a history browser. If not, please let me know and I can start over. So let's compile again without these warnings that we don't really think we need, and all the other warnings are gone. So this is really cool. What we did is compile a library that is somewhere here. There it is, right? So you got the shared object, static version of it. And what we also got is a whole bunch of examples. So by now we have really a lot of examples, which our first effort at having some kind of documentation tour was something we did a couple of years ago. So there are 4 steps, each of which is a certain problem that we solve, from just reading some third-party mesh file to running a simple finite volume solver or solving a simple finite element system. So this is a good starting point if you want to look into how we may be using Pforest from primitive applications. So those do some very primitive numerical things that we do ourselves, but of course you can use your own numerical linear algebra to be a bit more professional on the discretization and solver side, right? So what else is there? So there's example points. That is something that I don't show very often. So maybe I should just run this. So I should change into this directory and use one process for now. And you see that we have prefix P4 and prefix P8. So the first is a 2D version, the second is a 3D version of the compiled code. Did I have options on this one? No, I did not. So we get some hints here. So if I understand the program that I wrote many years ago, let's, for example, do a Möbius strip as geometry, refine to level 4. Then there is max points and prefix, which let's see what happens. Oh, this program requires a file. So this file is in the source, of course, or not. So I am thinking I should investigate that later and go into a different example. Steps, for example. So this is a very simple thing, and our programs usually don't print all that much. You can disable most of the printing if you want to, so you get the version numbers, which I think is important, but even that not really everybody needs. And then here you get what's happening on the top level of the mesh calls. So we have a new call where we just create our mesh, and then we do things with the mesh. So we would refine the mesh, we would partition the mesh in parallel, and you see that from refinement we go from 1 element to 910 elements. So this is probably a recursive refinement call, since each refinement in 2D just gives us 4 times as many elements, and here we apparently do many of these things in one call. So this is a recursive refinement call that we did. And there are a couple more things. So how can we figure out or get a better idea of what happens? So we get as a result, we get files here. So those are files according to the VTK format. The VTK format is a format that can be read by many visualization softwares. For example, ParaView. So this is a ParaView window. And I can open these graphics files, and I was just building build Mpi here. So we are in steps, and let me open this file, and you see I got some result in green, which makes more sense if I color by refinement level. So this is an exercise in refining based on some graphics file. So how did we get here? for this, we should probably open an editor and look into this example file. This is a program. So you got all this in just about 200 lines of code, and a lot of that code is documentation. So let's say you can do these things with maybe just under 100 lines, which for this functionality is, I think, a pretty good compression of effort. So like this. Oh, this is, oh, it was out here. Yes, thanks for the tip. Thanks. Yeah, so this works, right? Okay enough? Mm-hmm. Yes, so if I full screen this myself, it is somewhat blurry, but it's not terrible. If you want to look at this yourself, you can of course grab the code, do the clone, right, and open this in an editor yourself. You see up here I'm in step 1.c. I should put on the line numbers here, but it's a short program. So if you can't read this, please check out the source code. What we do is calling Mpi init in a C program, and you see that we did a little bit of wrapping here. So we have this prefix, which means we want to be able to call Mpi init even if the build is without Mpi. So I could configure the software without Mpi. Maybe I should do it right now. So I'm compiling this thing, the same source, but with different options. And to remind myself how I did that, I can look at the first couple lines of the log file of configure in that other directory that I just built. And then I kind of just borrow this configure line, except I'm not using MPI here. And also the quotes are gone. So this is the no MPI window. This is the MPI window. You see in the bottom here that there's a bit of a multiplexing terminal. So this is terminal number 4 here. And there's terminal number 5. The only difference is that here I do not configure MPI. Otherwise it's the same thing. And the source only exists once, of course. So if you're in an Mpi compile, this will call Mpi init, and if not, this will do nothing. And this is something we accomplish in our SC library subdirectory, right? So you see that we have these all these things that replace MPI in case there is no MPI installation, but we still want to have some dummy functions. So we don't need to if-def in our main program. So we would just do nothing if we do not compile with MPI. You see here, so if we don't have MPI on configure, then we will just replace the appropriate calls. So that's what we do here. In the meantime, we should make this so you see the same programs here, except here they are not linked into the MPI library, and here in the previous terminal they are. So what if I run this in parallel, say with 9 parallel processes? You see that nothing really changes. We still get 910 quadrants or elements, but then we call partition, and partition basically distributes the quadrants in parallel again in a way that is fair, because refinement is usually not fair in terms of some processes get way more elements than others. So we would want to call partition, and the result we get here is another bunch of graphics files. This time we get 9 files, 1 from each process. not just one file as earlier. We could repeat the visualization and we could color by level as before, but we could also color by MPI rank, the process number in parallel. And you see that we have processes from 0 to 8 inclusive. And the colors are hard to tell here, but you can roughly see that the number of elements per process is about even. And this is what we get from partition. So let's walk through this. There are a couple init calls, and this is something that's not super well documented and somewhat confusing. So it is okay not calling these functions, right? It's not like you have to do these obscure things, especially these one options here, install some hooks for back traces and things, but if and abort handlers and so on. But if you're using Pforest from a library, you may want to look at the source code of this one and pass zeros here, so we do not mess with your exit handling, your back traces, and things like that. It is a good idea to call this and providing your MPI communicator, because this will make the log messages be depending on the rank. So here in this program, all the log messages were from process 0, but sometimes you can of course log from all the other processes, and this thing will give you the correct number in the log message. So it is, I would say, call them, but sometimes you may want to disable these extra hooks here. Check out the source if you want to. And now we just make a square as an initial mesh. So the square is one tree. What about trees in Pforest? We call it forest because it's one tree or more. And the best thing here is probably to illustrate one of the tutorials. So I'm back to my school webpage here. Then you see the build tutorial, which is just roughly what I've done with the smallest recommended main program here. So we kind of covered that. And then there's a difference between connectivity and forest. So connectivity is setting up the roots of the forest. So each root in 2D is a square, which you can think of geometrically as being some image of it. And in 3D, each root is a cube, which you can deform for your application geometry, but we do not need to know about these geometric mappings. What we care in terms of the tree roots is the topological connection. So if we click on this, you can read up here. You see on the left here we have a 5-tree connectivity in 2D that is embedded in 3D, and we have one twist to make this a Möbius strip. You can create this example with example/simple. So here you could run simple with the option to create the Möbius geometry. I recommend actually that you try this and visualize this output with the visualization program here, right? Of course, we need to somehow begin by connecting all these trees. So for each tree, we have to tell the software which of these faces connect to the domain boundary and which of these faces connect to a different tree, and if they connect to a different tree, which number of that tree and which way around in terms of which face, right? We can rotate each tree in 4 different ways, and we can, in addition to rotating, we can flip. So in 2D there are 8 ways of connecting 2 trees or one tree to a given face of another tree. So our connection is relative to the me tree. What is my view, the perspective, and then there's the other tree, which is to be connected in 1 out of 8 ways. And this you can prefab those. So here you can just call unit cube, which is a function where we do all that. But it is worth, and for understanding the forest of octrees is absolutely essential to look at the definitions of how we connect trees. So I have linked in this tutorial the 2D connectivity object documentation and the 3D connectivity documentation. So in 2D, this is some of our source files here, and you see that the connectivity is really just a block of arrays, and they are documented in some way. What's really interesting is this yellow block here, because this is the best way that we could put this. Basically, I wrote this way in the beginning, 2007, and it has not changed, right? So that's not true. I think at some point we actually did some right-hand rule ordering, but we quickly found that we don't need to do that. We should be Z order or lexicographic relative to the trees. So what's obvious here and what is not obvious? What's obvious in a way is how many trees we have, and so those things are not obvious. I'll tell you why in a minute, right? So this is the first obvious thing in this object. Then that's the next obvious thing. For each tree we have 4 faces, and for each face we say which tree is on the other side. If there's a domain boundary, we just put in the same tree. But if it's a real tree, we put that number there. The next third obvious field is tree to face. So similar to the tree number we have on the other side of our face, we need to know which of the face numbers are on that side. So there are 4 different ones. And to encode the additional possibility of flipping, we have 8 options. So you can give this tree to face number 8 different values, 4 without the flip and 4 with the flip. And this is encoded and described up here. So corners are not obvious and vertices are not obvious. Why? Vertices are really just for being able to primitively visualize this, right? When Lucas wrote that first VTK export, I think, we needed the vertex positions for the viewer. So what we do here is give each corner of the tree a position in space. Of course, we are free downstream to ignore this, say our simulation has a different idea of the geometry. But this is important. Suppose we have a mesh that is self-periodic, right? We have the all-periodic unit cube. Then topologically, the 4 vertices are the same thing in terms of connection and topology, but geometrically in terms of where to display it, those 4 points are different. So what we put into vertices is not the topological identity of a vertex, but just the position we want to represent this corner of that given tree for visualization and maybe for your geometric functions in simulating things. So this means that, for example, when 2 trees come together, we can give those 2 corners the same vertex number, but we don't. Here we really always have redundancy in this information. Since this is not about topological identification, this is just convenience. And here there are the according coordinates for this, right? What is topological is the number of corners. So a corner, the idea is that a corner is the same thing if it's the same topological object. So for an all-periodic cube, we have 1 corner which is identical. It just geometrically has 4 different positions, right? So in an all-periodic mesh, we would tell this connectivity has one corner, and then this corner has multiple things that it connects, and that is encoded here. So for each tree says 4 potential corners. Here's the question, how do I visualize? This is the ParaView software. But visit works too, since the VTK format is universally defined, so you can use any viewer that reads that. So here we would, this tree has 4 potential corners, but in this case we would put 4 times the same number namely number 0 for the first corner, into this field. And since each corner may have multiple, may have a certain individual number of trees it connects, in a periodic unit cube, each corner connects 4 trees, effectively, which is all the same tree, but from a different corner, right? So in this case, we have 4 trees for this connected by this one corner, so this offset would be 4. And then here we actually collect for each corner all the trees and the corner of the other tree that is meeting here, right? So for an all periodic cube, we would meet the same tree on the other side, but a different corner, and in this case, corner is relative to the number of the corner within the tree. So I think you may need to look into that if you really want to understand this, because this basically allows you to encode a periodic mesh, and the application software never needs to know this. So there's a lot of application software that has problems with periodicity, because you need to be special on the boundary conditions, you need to be special on numbering, special on certain other indexing. And here, if you just tell on one side of the tree is another tree, then it doesn't matter if it's the same tree rotated, for example, right? And the application software will never know that there is anything periodic in this mesh, even though effectively we can connect it in a periodic way using this structure. So this is in a way unique to Pforest, this encoding. And the good thing here is you can look to a couple examples. So let's do this in 3D, where in addition to corners you have edges as a topological thing. And you see the unit cube is probably the simplest thing, but then there are more. You can have some strange thing out of 6 cubes just for the hell of it. Certain things that all have some funny rotation in it, here and there. And you see they get a little more interesting with all these fields, right? This is a shell, so this does 24 cubes that together make up a hollow sphere, things like that. And the periodic wondering where the periodic unit cube is. I think it's in 2D. Here. So this is your example. This is the periodic unit cube in 2D, which gives you a very good idea about how this encoding works. If you want to read a mesh from, say, a mesh generator, and want to use this as a root connectivity, you will need to translate this into our convention. So that is somehow the biggest hurdle in being general with Pforest, is understanding precisely those documentation blocks. So once this is done, everything else follows in the sense of neighboring and the numbering and the conventions of how do we encode rotations and flips and other neighbor. Excuse me. Just helping out with the visibility here. Of course, this is not great to see. I agree. I will upload these videos, and I would think that these videos are sharp, so you can fast forward and see what I do. Also, this file is linked from the web page. So what I'm basically doing here is going through the web page and clicking on things. So you can do that yourself on this conference web page. And for example, I was just clicking on some of these links that go into the GitHub representation, right? So this is a bit of a unique thing, the connecting the roots of the forest in a way that is more general than many other codes that I know of, especially with this periodicity, for example, right? So you can encode a client's bottle with this thing if you want to, and the numerical simulation code will never know the difference, except if it has some kind of notion of vector fields And when a vector field goes from one tree into the next, of course the coordinate frames are different. And I guess Donna can tell you a couple things about how she experienced these changes of coordinate system from one tree to the next tree, because logically each tree has a lower left corner standard coordinate system, but then the next tree is connected in a different way. And all of this follows from this very small convention block, so it's recommended reading. We are almost to the full hour now, and all I did was basically building the code and going through a very simple example. But that is actually part of the uniqueness of Pforest to work with the connectivities this way. Of course, you can just have an easy life and create a cube or a square, and with this root, you can actually create the forest itself. Forest means creating the actual elements by refining the root one or more times, uniformly, adaptively, and these things are done with Pforest_new. We have actually in the past extended those. So functions that are not easy to find on the first try is those favorite Pforest extended files. So in this file we have updated versions where you can parameterize more things. For example, would you want the tree to be uniformly filled on refinement or not? So this thing creates your first instance of the forest object. I have a couple questions here, so sorry if I read them rather late. So if you want me to respond earlier, please just talk into your microphone. Then I don't. I'm quicker. But let me read this. So glad most people can work with the video software here. So when I mean cube, I mean square in 2D or cube in 3D. I also mean when I say quadrant, in 2D it's a flat square element. In 3D it's a cubic 3D element. So it's all what it seems to be depending on the dimension, and all of this is pretty much the same thing if you do it in 2D or in 3D. Many of the concepts are identical. The font sizes, again, if you have a big enough screen, you can just try. There's in this web interface on the top right, there are four white arrows like that, and if you click on that, you can have a full screen version of what I am sharing, which is blurry but reasonably okay. And again, these files are all in the code, and if you go to the examples, you can just find your way from one to the next. So another question, how to obtain the splits in the initial geometry. The initial, you can create a forest that is just not split at all. You have just each tree root is the biggest possible element, and then you have as many elements as you have trees. You would achieve this by calling Pforest new X here with whatever connectivity that you have created before. I would strongly suggest to set min quadrants to 0. This is a bit of a legacy thing that I'll explain later. You would just set minimum level to 0 and fill uniform to 1. So this means that you do not refine initially on creating the first forest of quadrants. You would then refine this later, but initially you can work with this for a while if you want to. Right? So the initial split is parameterized here, but what I usually would do is create a uniform mesh at some level, say 3 or 5 or whatever seems reasonable. But if you have connectivity with 10,000s of trees, you would not want to refine in the beginning, but even the first refinement should depend on refinement indicators that come from your numerical code. Yes? Mm-hmm. So the question was for the recording here, how, if I have a geometry such as a torus, for example, how could I obtain initial splits and so on. So it is up to you how you initially divide the torus into a certain number of trees. So if I were to create a two-dimensional torus, I would make a square hole in the middle, and then I have those 45-degree trees on the outside. So with 4 trees, I would make a 2D torus. With a 3D torus, it is up to you how you think you would best create this as a map of multiple connected cubes that has the minimum amount of distortion and the highest amount of symmetry. So this is up to you in a way to get a piece of paper and draw your torus, and then find a way to say, I define my tree roots in the following way. And then for each tree root, you would define a coordinate system, yet meaning decide for each tree root where is the lower left corner relative to your general orientation. And then you slowly begin to make a table on paper, like which tree connects to which other tree on which face, and so on. And then you will have eventually assembled the connectivity for this torus. You could alternatively use some mesh generation software to map your torus into cubes, and then write a translation into our data structures. Mm-hmm. Mm-hmm. Yes. Yeah. Mm-hmm. So the question was, how can we create connectivities? Say, if we begin with a cube, could we change this into a different form, say a brick shape or a rectangle or something? The answer is no. If you want a rectangle that is 2 by 5, or in 3D 5 by 7 by 19 or so, you can actually either put this together yourself, or you can call a function that Toby wrote actually in the beginning. There's a new brick. Yeah, new brick. So this is exactly what you asked for in this case, right? So it's a rectangle of some dimension, m by n, and you can have this in 3D, and you can say if it should be periodic in any dimension or not. So suppose we had not written this new brick function, you would basically need to read that documentation block and allocate these arrays according to our convention. No, this creates m times n trees. So a connectivity is always one or more trees, and most of these functions create more than one as examples. And you are free to create any number of trees in your own connectivity if you don't find it here. Mm-hmm. Yeah, those are special cases where you really get just one tree. Once you have created the connectivity, you cannot really change it during your simulation. You can change the refinement, but the topology of the simulation in terms of how the trees are set remains the same. I would recommend actually to go through the connectivity tutorial. So there's a question, will I go through all the examples? And naturally the answer is no. This was 1 hour out of 3 that I have, and I'm really at the complete beginning in some way, right? So which is good in a way, because there's so much to tell here. But I'll of course do some zooming in and fast forward in the next 2 lectures. So I will not get through everything. Lots of this is really up to you to go through the examples, the exercises here in connectivity. You find 2 exercises that will get you fairly far even if you just want to have an example and make a copy and make just some connectivity that you like. For example, you can make a 3D torus if you want to, right? And work through the documentation block until you actually see the 3D torus in the visualization. Of course, it may be a square torus, because it's not about geometry or smoothness, it's about topology, right? But if you have a torus, this is logically a torus, even if it's a square or a cube with a rectangular hole or something, then this is a successful exercise. So maybe this is a good point to stop here, since Toby's up next. So until tomorrow, 17, you will have had more input from Toby, and you can just divide your time and do some learning by doing here. So there's a bunch of material, and we'll be very happy to answer questions and to do a lot of Q&A in the sessions. But really the best thing is for you guys to get going and grab a favorite problem or example or anything, and work as much as you can on this and get back to us. And we have several days, and if you guys can do this once out of these 4 afternoons or mornings, then I think this will be a very beneficial thing. Any more? Yes, I see iterate and L nodes, so I will definitely go into more advanced high-level functions on Wednesday, and maybe relate to it in the theory session Tuesday. Thanks for your comment, Daniel. Okay, Toby. Thanks to everybody. Any very last minute question right here? Mm-hmm. Mm-hmm. The mesh quality is something that we do not have a concept of. So if you create your connectivity that you have very bad aspect ratios, for example, then you will have that, you cannot fix that with refinement, since refinement is isotropic. So if you have a domain that is 5 by 3, it is a lot better to really use 5 by 3 trees to have a good aspect ratio, instead of having one tree and warping it. So the aspect ratio and also the amount of distortion in your initial mesh is relatively important for you to consider, to see, is 1 tree or 5 trees or 10 trees enough, or do you need to be really fine? I have some guidelines here. Please read through the connectivity tutorial. This may answer some of your questions. Okay, thanks very much. Sorry for running slightly over. Toby, welcome and thanks for your participation. I'll make you presenter in this software. So I will stop sharing my screen like this, and then you will have, now you have a button on the bottom right next to the camera button, which you can use to share a whole screen or a window.